Hello, I'm Isabella Bargula, and this is my project explaining the methods that are used to produce and deliver energy to our homes. In addition, I will touch on an alternative energy source, hydroelectric power, and will cover the similarities and differences between the two types of electricity generation. In traditional electricity generation, coal is used as a fuel and chemical bonds are used as a source of potential energy. First, coal is brought in from a fuel supply area and is pulverized to form a fine powder. The pulverization of the coal increases its surface area and allows it to react more completely and release more energy in less time. The coal powder is then blown into the combustion area, furnace or boiler, and is suspended in the fire so the reaction can be as efficient as possible. During this process, chemical bonds within the fossil fuel are broken down and release their energy in the form of thermal energy, or heat. Next, heat from this stage heats water in nearby piping. After the water is transformed from its liquid to gaseous state, its pressure builds up and is channeled towards a turbine. The turbine has a shaft that is connected to wires within a magnetic field. Hot, pressurized steam blows through the turbine, causing it to rotate and spin the shaft with it. The constant rapid rotation of the system causes an induced AC current to its source to be heated again, and the induced electricity from the generator travels to its next step, transmission and delivery. When electricity leaves a power plant, it first passes through a step-up substation. At this point, the voltage of the electricity is increased so that it can travel over long distances. This is done by passing the electricity through a step-up transformer. These transformers are another example of how electrical induction is used. An alternating current flows in one side of the transformer with fewer turns about the iron core. As a result, an oscillating magnetic field is induced and induces an EMF in the secondary coil. The secondary coil has a higher amount of turns, so the induced EMF is higher than the original and is altered according to Faraday's law. The electricity now has a high enough voltage to be carried over long distances in transmission wires. Although the wires used are conductive metals, meant to have very low resistances, power is still lost along the way. To remedy this, step-up transformers are placed to up the voltage from time to time. Energy traveling through these wires typically runs at 115,000, 230,000, or 500,000 volts. When the electricity comes closer to its destination, it passes through a distribution station containing step-down transformers to bring the voltage down to a lower level for increased safety and decreased cost of delivery. Step-down transformers are the opposite of step-up transformers. The same physical principles apply, except in reverse. The incoming side has a higher amount of coils, and the outgoing side has a lower amount, so the magnitude of the voltage decreases. Next, the energy leaves the distribution station to travel through delivery wires, or traditional power lines. The electric potential at this point is approximately 15,000 to 20,000 volts. Finally, the electricity passes through a final step-down transformer that brings the electricity to a safe voltage between 240 and 120 volts. A service drop wire then connects a house or building's power meter to the source. Once the electricity reaches this point, the house or building will be able to freely use electricity. One issue that power companies run into is the efficiency at which electricity is created, transmitted, and delivered. Almost 2/3 of the potential energy stored within the bonds of fossil fuels is lost between the point that it is burned and the time that an electric current is induced within the generator. Efficiency could be increased in this stage by increasing the insulation of the materials housing the combustion area and steam pipes, and improving the design of the turbine generator system. Also, a lot of power is expended as heat while traveling through the transmission wires, so efficiency could increase in this area by finding an alloy or compound that has a very low resistance. Hydroelectric power creates electricity by using the same physical laws as fossil fuel-generated electricity. However, it harnesses a different type of energy. Instead of harnessing the chemical energy stored within the bonds of hydrocarbons in coal, it harnesses the kinetic energy of moving water. First, water is held in a river or reservoir, and a dam is built adjacent to it. A canal inside the dam, called a penstock, then guides water down to a chamber that houses a turbine. As the water descends, it builds up speed so that it hits the turbine with enough force to cause it to rotate. In contrast to fossil fuel, in which the wires spin, massive magnets spin around the wires to induce an EMF and send an electric current to homes and buildings. After the water has passed through the turbine, it flows through the output area of the dam and continues down to a river or other body of water. Also, unlike coal-based power, this water cannot be reused in the same dam unless it is returned to the initial reservoir. However, like fossil fuel, the energy created goes through the same process to be delivered to homes. The energy also is stepped up, transmitted, stepped down, and delivered. Hydropower is also a bit cheaper than coal-based power. In the U.S., the average cost of hydroelectric power is 85 cents per kilowatt hour, which is about 40% less than coal power.